Hello, my name is Jovid and I'm going to show you a tool for creating paleogeographic maps which is called Terra Antiqua. Terra Antiqua is a plugin for QGIS that allows you to create paleogeographic maps. But let's first look at G-plates, which allows you to rotate continental blocks to their past position. I'm not going to dive into G-plates. I assume that you already have some ideas about how to use G-plates. But G-plates allows you to rotate tectonic blocks to their past position and export it in a GIS compatible format so that you can use it in QGIS to create paleogeographic maps. When you export it, you get files that contain rotated tectonic blocks like this. So you can get topography, you can also get reconstructed paleobathymetry rotated to the time of reconstruction. Or you can also have age grid and so on. But all these data that you get are separate and you need to compile them and further modify to create your paleogeographic maps. Because paleogeographic map is not only about rotating present-day geographic features to their past position, but also modifying them, modifying the elevation of topography or modifying the bathymetry values. So Terra Antiqua allows you to do this. First of all, we will compile all this data in one single raster digital elevation model that we can use as a paleogeographic map, as a basis for our paleogeographic map and modify it. So these are the tools of Terra Antiqua, the plugin we are talking about today. So the first one is compile topobathymetry. It allows you to compile these rasters that we exported from G-plates. Let's go into it. And when we click on it, a dialog will open which has a help text on the right side which you can read to see how the tool is used and what data you need to input in order to get a single digital elevation model, a single raster with your data. So the first thing is continental blocks that you need to select. These are the masks with continental blocks and continental shelf and shallow sea regions. Here we can see them. I have them merged in one shapefile which include continental blocks, continents. We also have shelf zone, continental shelf zone, and then we have shallow sea bathymetry. So these masks are inputted in our compile topobathymetry tool to compile the rasters. So the tool knows where, which type of data it should put. So let's select general mass, then we need to select our eTopo bedrock topography, and we can also select reconstructed bathymetry. Here I'm using a reconstructed bathymetry by Mueller et al. 2008. You can also use ocean age, but ocean age grid that we have today doesn't contain the ocean bathymetry which had been removed during geological processes. For example, Tethys got removed during subduction beneath the Eurasian plate. So these areas are not covered by ocean age grid. That's why we can use reconstructed bathymetry for these areas. But if you have ocean age, you can also select ocean age grid. These will be combined. And you can also specify shallow sea bathymetry. If you don't want to use it, you may keep it empty. But the items which are marked with star, they are mandatory. We then specify the maximum depth of continental shelf today and the age of reconstruction. The age of reconstruction is actually used to calculate depth values from the age of ocean. So if you supply age grid, then you specify age of reconstruction. If you did not supply it, then you don't need to specify. And in order to avoid overlapping bathymetries with continental blocks, so that sometimes you get between two different rotated continental blocks, you get empty spaces which overlaps with bathymetry, and bathymetry values will be kept in those areas which shouldn't be there, and it's actually an artifact that should be removed, so we can remove it with this option. If you specify an output file path, your file will be saved on your disk where you specify. If you do not specify, then it will be saved in your temporary folder and added onto the map canvas. But keep in mind that if you choose this option, when you close QGIS project, then this file will be removed from your temporary folder. So do not forget to save it prior closing your QGIS project. Then we run it. And here we can see our progress in the log tab. It doesn't take much time, it should take about a minute, but it will take different time on different PCs based on the power that is available on that PC, on the computing power. But we need to wait until it finishes and adds our resulting raster onto the map canvas. Okay, so now our raster has been compiled and added to the map canvas. Here we can see that our result is saved at temporary folder because I didn't specify any file path for it. So let's look at our map now. So our compiled map now looks like this. It combined all the data we supplied, including bathymetry and topography, and even applied a color scheme to it so that it looks more realistic. Okay, so then we can use this raster file, this digital elevation mode, to further modify and create our final paleogeographic map. Okay, we will continue with modifying topography values that we have here. So we have some topography values. We have topography, we have bathymetry, but at 38 million years ago, the time we are reconstructing a paleogeographic map for, at that time we didn't have so high mountains in Tibetan Himalayan area or in Andes or in Cordilleras. So we need to modify this topography to be lower. And for that we can also use masks. We draw some masks over it, which is kept inside a shapefile as polygon features. And each of these polygon feature has a formula associated with it, which we can use to modify our topography. So here we have formula, here we have some min and max values, which I'm going to explain a little bit later. Okay, so let's run our tool for modifying topography and bathymetry. This one is intended to modify topography and bathymetry. So when we run it, we can see that we have here a topography raster for modification that we need to select, and that raster would be the compiled topobathymetry raster that we just created by compiling our raster data. Okay, let's select this raster and then select vector layer containing our masks. As I showed you, this is topography modification masks layer. And so in that layer we have a bunch of polygon features with formula associated with them, and that formula is actually kept inside a formula field. So here we need first to select topography modification mode. We can modify with formula, we can also modify with minimum and maximum values by rescaling. And rescaling actually rescales our current values to fit inside the final minimum and maximum values. So let's modify it with formula for now. We select here, we can type one formula if all the polygons must be modified in the same way using a single formula. But if we have different formula for each polygon, then we can select a field in our attribute table that contains that formula. So after we select the formula, we can actually constrain the values to be modified. We can modify only those values which are, for example, between 1,000 and 2,000 meters, or between 1,000 meters and 8,000 meters, you name it. But in this case, I'll just modify all the values. So let's run our tool and see what we get. So here you can also see the log tab with some warnings that tells you that some polygons in the input vector layer overlap each other and they will be modified several times. You should avoid this. You should keep your masks separated so that they do not overlap each other, so that you do not end up modifying one area twice. Or for example, here we can see that mask 6 does not contain any formula. So keep in mind that that area is not modified. Okay, so let's see at our map. We can see here that it is modified. So paleodem modified topography. I just move it to results group to see it and switch off my mask to see my resulting map. So we can see that the area is quite nicely modified and the values are lower than present day. If we compare it, we can see how it differs from today's topography. Okay, let's move on and for example create a sea right here. We see that Tethys area is still empty because the oceanic basin here subducted and erased. So we may interpolate the values for this area, or we can also create a sea here. So for that I already have drawn a mask to create a sea right here where the Tethys is, and we can create a sea or a mountain range using a tool here which is called Create Topography and Bathymetry. So let's again select a raster to be modified, and that would be our paleodem with modified topography. Then we can select our layer with feature polygons. These are the masks that show our tool where to create a sea or a mountain range. So in my case I have sea ocean creation mask. But before I do that, let me select this mask, because I have also a mask which is intended for creating mountain, not an ocean. So that's why I select ocean mask and go back again to my tool, select my paleodem modified topography, select layer with polygon features, which is my sea ocean creation mask, and then I already have here an option for selected features only. If I click on it, only selected features will be used to create the geographic feature. In this case, I'm creating sea. And here we have some values that specify geometry of our feature to be created. And this is maximum sea depth, minimum sea depth. So maximum sea depth is actually the maximum depth of the oceanic plateau, and minimum sea depth, the minimum depth of the oceanic plateau. We can also have maximum shelf depth, so the shelf zone does not get as deeper than this value. And we can also specify the shelf width. As wider we specify the continental shelf zone, as bigger our ocean should be. So if we are creating a huge ocean, then we need to specify wider shelf. If we are creating a small sea, then we need to specify a narrower shelf zone. So let's specify it for now as let's say 50 kilometers. Then we can have our continental slope, which we can also specify as, let's say, 50 kilometers. Okay, and then we run it. Here in log tab we can see which geographic feature is being created. Okay, so then we end up with this Tethys created in the area we specified. It's deeper, so we can see also the areas with shelf zone and with continental slope and then oceanic plateau. So it used our values to create this ocean. Okay, let's create a mountain actually inside the Africa. So here I have drawn a small polygon to create that mountain, and I can run this. Well, first let me select it. I can select this feature, but I need to highlight my layer. Okay, I select this feature, and then I go to creator of geographic features, and I select my, now I need to select my last lastly created paleodigital elevation models, which I created a sea on, an ocean, a Tethys sea. So I select Paleodim with created features, and then I need to select my mask layer, selected features only, and then I need to change the option to mountain range. So now here I'm creating a mountain range. I don't want it to be so high as 5,000, but I can keep it like as high as 2,000 meters. And the minimum ridge elevation, so the maximum ridge elevation is the maximum elevation of the ridge itself, and the minimum is the minimum elevation of the ridge, the mountain ridge. So let's keep it 1,000, and the rigidness of the mountain describes of course, the rigidness. So it introduces random rigidness, so it looks more natural. So I'll keep it 30%, and width of the mountain slope, I will keep it the mountain slope. You can, if you specify it very wide mountain slope, then it will be like a plateau, for example. So here I'm creating it like with 5 kilometers. I'll keep it as in default. I'll keep the default value. Okay, so let's run it and see what we get. Okay, so now we can see that a mountain is created right here. Of course, it doesn't look so natural, but you may think of better values, of better maximum ridge and minimum ridge, the values that you need specified to create this mountain. We can look at it in 3D. Let me bring it back and select this one so we can see this mountain that we created. In 3D looks more natural than in 2D. So this is the mountain that we now created. Okay, let me return back to the raster. Then when you finish modifying, when you finish creating your geographic features, then you can actually finalize your raster. Of course, you can remove artifacts using this tool, and you can smooth it, you can interpolate it. But let me just finalize our map with filling the gaps. First, I need to fill all these gaps that are remaining by interpolation. Let me select my Paleodim with created features, and then if you want, you can interpolate only inside polygons, but I want to interpolate in the whole raster, so I'm not specifying the masks for interpolating inside them. And also you can smooth it if you would like. For now, I'll just keep with interpolation. Run it, and voila, our features, our map is interpolated and the gaps are filled. And so then we can, if you like, you can also smooth it so that the abrupt changes between topography values, like here, because we had different masks and different modification formulas, so these abrupt changes get smoother. So let's go to standard processing tool here and select smooth raster. Then I need to select our latest raster, which is Paleodim interpolated. And here you have two options to select from: Gaussian filter or uniform filter. Then you can specify the smoothing factor. As high a smoothing factor is, as smoother your raster gets. For now, I keep it, the smoothing factor is 1. Let's run it. Okay, so our raster is now smoothed and it looks much better than before. And so you can then use this map as your paleogeographic map for the time of reconstruction. Let's have a look at it in 3D. So this is our Tethys, which we created right here. It's very deep. It should of course be shallower because it's very narrow, but if you specify different values, you can get different depth of the ocean. Okay, so my time is limited. For this video, this will be all. If you have any questions, go ahead and ask.